Hello, welcome back. Now we have the much anticipated student presentation that your advisor Alex recently told us will be awesome by Viet Dung Nguyen on dynamic prior preference learning for scalable, robust, deep, active inference. So, thank you, Viet. Take it away.
Hello, everyone. My name is Viet. I'm from the Neuroadaptive Computing Laboratory, Department of Computer Science, Rochester Institute of Technology, and I am Alex Advisee. And today I'll be talking about dynamic prior preference learning for scalable, robust, active inference. So, yeah, first of all, want to talk about the motivation for this. So nowadays, frontier work in robotics excels in implementing robots' behavior and planning. For example, creating autonomous robots that can actively explore in the environment. Additionally, we can also do a lot of robotics applications. For example, acquiring knowledge and learn skills continuously. Um, and this also envisions cognitive and developmental robotics. So there's just a goal for robotics research. That we can try to build a robot that can continuously develop through interactions with the environment and their learning processes. And it is also better to have interactions with their physical and social world in a manner of human learning and cognitive development. So there's a lot of robotics applications around. And for example, one application can be to build a safer robots and um, building social collaborative robots and stuff like that. So underlying all these robot work, we it's like active inference research where we often build a generative models. It's so the development of robotics actually depends a lot on active inference framework because there's a great need for research that integrates the generative world model into robotics control system. As also deep learning is increasingly used in constructing complex action planning algorithms for solving control tasks. We can see that there is a need for scaling active inference systems, especially a deep active inference system to integrate into the real world applications. So research in active inference has led to many improvements in terms of robustness of model-based agents that applies to both Markov-Decision processes and partial observable MVPs or POMVPs. An example of an MVP environment would be mountain car. For those who knows or studies reinforcement learning already, then this mountain car environments in MDP, we only know position velocity, right? And that is the actual state of the environment. But when we get to POMDP, for example, like robotic tasks, we as agents see only the image frame, and we do not know the underlying states such as position and orientation of the block or joint states of the robots, for example. Right? So basically, active inference is basically a form of inference and learning that seeks to balance, first of all, the goal-orienting objectives or prior preference. So this signal exploit the instrumental signal so that the agents can seek the goal and try to pursue its goal. And the other thing, it needs to balance the epistemic terms or epistemic signal where the foraging, it cares about foraging and exploration driving signals. So researchers often actually encounter great difficulty in providing the agent with effective prior preference, as well as computing useful instrumental signal from the agent's the priors, especially in the real world applications where the environment is very complex, the robotic control task, and the trajectory or pathway to be desirable and task-specific goals often requires a very, very long trajectory of preference. So it is not that actually practical to provide a prior preference distributions, especially the stream or rollout of goal images. So that is the reason why we need to find a way to also learn to generate the prior preference signal in active inference. So on the right here is just our preliminary results, but we'll get to that in a moment. So yes, so we actually, given with that all of this, right, we need to predict a draw out trajectory of a goal state dynamically, right? It can be a goal state or goal observations, but basically the goal is, if you look on the figure on the top here, the top row is the real trajectory where you see the mountain car, right? There's a car that it needs to go backward and to build some kind of a momentum, and then go full to the right to get to the flag. If it is only going to the right, then it does not have enough momentum to go to the top of the hill. So so in here is the actual observations. You can see that the trajectory is a successful trajectory, and the goal here is to for each observation at each time step we predict a predicted preference image or goal at that single time step, so that we have the instrumental signal or idea of what we are trying to learn, and then from that we learn the actions planning on from the prior preference signal. So in this talk, we specifically analyze this issue, the issue of prior preference learning in the current literature, and discuss potential resolutions for scaling the instrumental signal inherent to active inference by introducing the contrastive recurrent state prior preference, or CRSPP. This is the model learning framework that we also have done in the past. So this methodology frames active inference agents in terms of progressively constructing and adapting a prior preference at each time step. So this also facilitates the dynamic emission of a useful or dense, very dense instrumental signal at each time step. So we also study how our prior preference adaptation scheme, when operating jointly with the latent space-driven epistemic foraging terms, offers active inference agent a very nice flexibility in challenging problem contexts, such as sparse reward environments, and also composed of continuous observation and action space, for example. For example, robotic tasks, we often do not know the sparse do not know the dense reward functions in the actual real environment. We only know if the robot has reached the goal or not, right? And also all these environments has varying goal states. So we can also see that providing the or manually craft the distributions of goal is not very practical. So yeah, so here's the outline of this talk. The introduction I have just covered. So first of all, I'll just assume that everyone is new to active inference, and I'm just gonna briefly cover active inference background and deep active inference, and also cover a little bit about prior preference learning and problems of all those prior preference learning framework. And then I'm just going to go through the actual methodology, which is the dynamic prior preference learning. And then first of all is the world model. Next is the self-revision mechanism. And then next is the learning prior preference models. And then finally putting all of them together to make an agent. And then I'll show the results and then discussion. Okay, so first of all, I want to cover a little bit about active inference. So just a brief overview about how active inference work and what is the underlying theories behind it. So it is a mathematical framework that describes how intelligent systems or human interact with the environment. So it also describes the environment as the generative process, and the intelligent systems, or the agent, or us as a generative model. So active inference is built on top of the free energy principles. This means that we, as agents or intelligent system, continuously observe the environment and forming and correcting our belief or our own representation of the world. Um, so the generative process defines a real world environment here, right? Um, this is treated as the data generation process, where the information patterns are sensed by the agent. So you can see that's the um, hidden state underlying hidden states denoted as here. It's generate a sense of some kind of a observations denoted O, and this is also sensed by our intelligent system. So on the right here is the generative model, is the actual agent that we are trying to build on the intelligent system, right? The intelligent system also has an internal state, which is trying to estimate the generative process states. So this is called the prior, or the internal belief prior to the observations of the environment at a particular timestamp. So this is denoted as the random variable S, or state, and P of S here is the distribution over the random variable S. So this makes the agent's generative model. The generative model represents the agent's approximation of this generative process in this world by continuously seeing the observations, or making the observation O, and modified or updating its belief. So we actually call the belief as after being updated after making the observation for the posterior, because it is the posterior after making the observation, right? So in order to learn the model and estimate the posterior, we first need to introduce these terms. First of all is the prior over state, which is denoted as PS, which is also the distribution over state, right? P of O here is the model evidence. It is the distribution over the current observations, denoting how well is our model at predicting the real data. And in order to compute this easily, this is often written as the sum of probability of observation given every single state. And then next one is P of O given S. This is the likelihoods, and the probability. This is the probability of an observation given a state. So this is a function. It gives the probability given an input state. And then the last one is the posterior functions, P as given O, which is the posterior function that maps the observation to the states. So normally in traditional active inference, the posterior function would be the transpose of the likelihood matrix, for example. And deep learning literature, it is often called a encoder, and the likelihood here is a decoder. So how do we estimate the posterior now? We have to find a belief that maximizes the model evidence, right? Because at the current time points, there is only one single observation O here, and it is real, right? So P of O, P of that observation, it's gonna be 1, right? So it should be the probability of 1. And then we use the states to estimate the observations, and then it has to be the probability of 1, 2, right? So that arrives us at the conclusion that we have to maximize the model evidence P of O. So maximizing P of O is also minimizing equal to minimizing minus log P of O, right? Because it is minimizing the surprise. So in the beginning, we say that we continuously update our belief after making an observations of the environment. We call the belief after making an observation a posterior. This is Q of S, right? So to compute a posterior, we want to put in a, we just want to call this, any kind of distributions over the states. Then, for example, we can sample it, we can randomize it, right? And then we try to gradually trick this distribution so that it's used the highest modal evidence or it's used the lowest surprise. So how do we choose the actual posterior so that it yields the lowest surprise, right? So in minus log P of O, here is the actual minimizing surprise, that objective that we are wanting to minimize, right? So we can analyze it like we can do it with a Bayes theorem. This is not Bayes theorem, but Bayes formula or theories, yeah. And then to evaluate the surprise minus log P of O, we need to sum out the hidden variable S from the joint distribution POS. But, well, this summations, there's a problem, right? Because we do not know like all the hidden states, all the hidden variables in the environment. It is hidden from us, right? So it is normally very, very hard to sum up all these state values. So if we cannot sum it up, then we can try to approximate it. So first we introduce a posterior into this sum, right? We multiply both the denominator and the numerator by the posterior. So this is the belief that we are trying to trick, right? So in here, we're trying to trick this posterior so that we can minimize this term. So this gives us a weighted sum where S, the ratio POS, and over the distributions Q of S is weighted by the Q of S. This is like weighted sum, right? So according to the inequality of convexity, or Jensen's inequality, says that the convex function of the weighted means is always smaller than the weighted means of the same convex function. So you can see the convex function here is minus log of something, right? So minus log of something is just a it's just a parabole, something like here, and this is smaller than a weighted means of the convex functions. Also, we put this sum outside, right? So this is also applied to the context of probability theory, and then we can arrive at this, equations. So formally, it's called an upper bound. This one, right? A quantity that approach from the above, right? So this is also means that this is a free energy. When we find a posterior that minimizes this free energy term, we will have a chance of approaching the lower surprise points, which potentially increasing the model evidence. So after we have these terms right here, we can just put the minus inside, and then it's become this form. This is the conventional form that we call variation of free energy. And after decomposing this, we will have these two forms, which is the KL divergence between the posterior and the prior, minus the weighted sum of the log of the P of O given S, which is the posterior functions. Or no, this is likelihood. So basically, the KL divergence term is called the complexity, and the minus log P of O given S is called accuracy term, where the complexity terms compute how surprise our states, two state distributions, posterior and the prior, are far away from each other or not, right? And the accuracy terms defines how accurate our model is predicting the actual observations, right? So this is also relatable to the variational autoencoder, where we compute the loss of the variational autoencoder to be the KL divergence of the posterior and the Gaussian distribution with a mean of 0 and a standard deviation of 1. And then we also have the mean square errors of the actual predictions of the images, right? And then VFE and MFE is a little bit different than from variational autoencoder. VFE is variational free energy, and MFE is marginal free energy, as in the active inference tutorial, the paper. So marginal free energy says that we compute the KL divergence between the posterior and the prior, and the prior here is computed from the transition model, not the normal distributions of mean of 0 and the standard deviation of 1. So here is the general model of trying to build a deep active inference model, right? So here's, first of all, we're trying to encode, right, using the posterior functions. So in traditional active inference, this is the P S given O is the transpose of the likelihood matrix, P of O given S. This is normally learned with the categorical distributions and using Dirichlet conjugate prior. And then in the deep learning literature, this is often known as the encoder. That's often parameterized by the neural network. And then O here is often be an image, and state here is just some hidden vectors that we are trying to compute. And then next one is the likelihood function, right? So normally we text in the states of the agents, and then we're trying to estimate the predictions, the observation predictions, right? So in traditional active inference, this is known as the likelihood matrix or likelihoods per se. This is also learned with the categorical distribution and using Dirichlet conjugate prior. And deep learning literature, this is often known as the decoder that is often parameterized by a neural network. So as we know the variational free energies formula, the complexity terms KL divergence here, right? And the accuracy term is the minus log PO, right? Given S. So here we compute the KL divergence between the encoded states and the actual prior states here. And then next one, we compute the actual log probability of the predicted observations and the actual observations right here. And that makes the whole objectives where we compute the two objectives right here. That's also the variational free energy formula. So we just talk about how inference in active inference work, but there's more. We want to build an inference system that can interact with the world, right? So when it comes to interaction between the agent and the environment, we also need to have actions and also roll out in time step, right? So basically, we have another element here, which is AT. And remember, I also mentioned the transition model, right? So after we take an action in the world, we the world or the environment evaluates one step, right? And it changes its own state and then emits a new observations. And we as agents or intelligent system also try to predict, given the action and the current states, what is the next state, and this state is the prior over the states of the next time step, where we have not made the observation OT plus 1 yet. So after we have the ST plus 1 as prior, we do the same process as I have mentioned before. So we make observations, try to change our belief after making that observations, and then learns from the new observations to trick our prior into the posterior. So here we learn it using the variational free energy or marginal free energy formula. So as we can see from the previous slides, we do need somehow to somehow plan the actions to interact with the world. So if we're trying to minimize or surprise with the current observations, so in the action planning, we aim to take actions that minimize the similar free energy term in the future. This is often called as the expected free energy, by the way. So in here, we introduce some new terms, right? Theta is the modal parameters. The reason why it is here is because we want to also compute the modal, the surprise over the modal parameters, or the uncertainty over the modal parameters. So you can see that the expected free energy in the future is kind of similar to the variational free energy formula. It only needs another modal parameters, and given the pi or the actual planned policy or planned actions. So after a lot of derivations, right? I will not getting into like the real derivation here, but here's the end results. That's something minus minus the weighted means of the log p of ot, right? So I'll just focus on this term is because this is the goal of the talk today. So basically, this term log of POT is the expected free energy derivations of the instrumental term. So basically, this also means that we are trying to maximize we're trying to take the action that maximize the future observations that matches our prior preference distributions or what we want, right? So normally, to learn to take actions based to learn to take actions to align with what we want to see in the future, we often need to craft and provide the prior preference manually in advance, and then we take the action based. We take the actions that maximize the likelihoods given that distributions. But this is often not really practical in the realistic world, and because we cannot like craft the manual distributions like every single time we encounter a new environment or encounter a new task, right? So what we can also do is we can also provide a goal state or goal observations directly to the agents, which is more practical. But in the end, the prior preference distribution is very sparse, and this provides little to no learning signal to the agent. As you can see on the figure on the right and the left, right? So left is the prior preference distributions, and right is the single goal state distributions or goal state image. So what can you do to dynamically produce the prior preference, right? We can try to learn a prior preference model, right? That produce a goal image at each time step. So here is on top is the prior preference model that predictions, right? And in the bottom here is the model prediction of the future given the sequence of planned actions. So we are trying to say that we want to take the actions that have the rollout in the future's predictions matching the prior preference rollout in the future. So how do we do that? We first have to learn the model first, right? So in learning, we can try to say that each time we achieve a goal, then we mark the whole trajectory as the prior preference trajectory or the positive trajectory or expert trajectory. And then for each observation marked as goal, we use a deep learning, like another deep learning model to estimate that observations. for example, right? And then in inference time, we actually train when we train the policy planner to propose the actions, right? We make the policy planner proposing the actions first, and then predicts the future observation based off of that actions that is planned by the policy planner. And then we actually learn the policy planner based on the signal that is emitted from how aligns the predicted future observation would be to the predicted goal. Um, the predicted goal here is the actual prior preference model outputs, right? Um, then we train the policy planner with the mean square error or some kind of objectives that predicts some kind of objectives between the predicted goal image and the predicted future observation. So there's this problem where it exists between all these learning schemes because it is very computationally expensive. So it is generally expensive because we have to work directly with the images. So for example, in learning, we have to use a decoder of the prior preference model to actually predict the goal image at each time step, right? In inference time, it is also computationally expensive is because it has to learn from the images itself and compute it down from um, the back propagations will have to flow through the decoder back to the action planner. So here it comes to the actual methodologies. We actually use dynamic preference learning in the state space instead of the observation space, right? So first of all, I want to talk a little bit about the world model. So this model architecture is basically what I have just drawn in the background sections, but this looks with robots images. So in here we have the observations, OT, OT, and here's also the observation, the same observations, OT minus 1 OT. And we text in the encoder. Encoder is the encoder posterior. Text in the encoder, and we have the transition prior, and then we have the decoder, right? Encoder encodes the image in, have the states, and then decode the image, the state back to the image, and then computes the accuracy loss. Right, accuracy loss is minus log prop of the PO given S, as we have discussed in the variation of free energy sections. And then the complexity is the KL divergence term between the posterior and the prior, right? So how do we compute the priors? We compute from the previous steps states, and then we use the transition model to estimate the next state's prior, right? So that's how we can get the prior. So current work and popular works regarding the world model or generative models often integrates the model called RSSN, which stands for recurrent state space model in the transition model. So it's to zoom out a little bit. We are trying to integrate some kind of temporal information through time, right? So that's the state of the environment or the states that we're trying to predict be more accurate, and it carries more information with time. So for example, we cannot encode the enough information from just a single image because, for example, there can be like position and velocity, right? The velocity is acquired through multiple images and cannot be acquired from a single image. If that makes sense. So what we often do is we try to integrate a recurrent neural networks that takes in the previous states or the previous recurrent states h t minus 1, and then we also takes in the encoded observations, and then in transition we produce the recurrent neural network. We produce the current recurrent states, and also predicts the outputs to put into the transition model. And also, the recurrent states will also be served as inputs to the posterior network. Um, so that's basically the idea. And then the other way around, we could just do the model as normal. So in active inference, the agent takes in the actions that it believes that would lead to its preferred outcome using instrumental signal. To construct this prior preference, Pascal has, for example, provide a goal state observations directly to the agents. For example, Mazaglia in 2021 with contrastive active inference. We can also manually craft a prior preference distributions. We can also dynamically produces the preferred observation at each time step. But as I mentioned already, all these methods is one way or another very expensive, or it's very not practical, or in the real world applications, or it is very computationally expensive for dynamically producing the actual observations for the goals. So we can also use behavior cloning, but its trajectory diverges from the training trajectory due to small mistakes made by agents as well as environmental stochasticity, and also it is because of independent and identically distributed assumptions of positive expert data distribution. So we can we will kind of avoid it because it's not gonna be the same, right? So two distributions of the actual trajectories in the environment will not be the same as every single positive trajectory of the expert data. So to tackle this, we try to leverage a small quantity of seed imitation data to learn a neural network that's dynamically produce the preference over states, not observation, but states at each time step. So this effectively produces an easily generated dense instrumental goal signal. And we also design the agent such as that it moves according to the trajectory that is shaped toward its own estimation of the future states or future preferred states. So it's trying to nudge its own trajectory towards the imitation or positive data distribution. So as you can see on the figure on the left, so you can see that in behavior cloning, the actual trajectory diverges away from the actual imitation data, where the prior preference over the states trying to trying to be shaped toward the imitation data itself using the model signal. And RAIF is our agent, is called robust active inference. And it learns from both epistemic signal and instrumental signals. But in here, we'll just focus on the instrumental signals and how to construct it. So, yeah, so basically we use a decoder or the likelihood functions of the generative model to only visualize the preferred observations. Note that in training or test time, we do not use the model learning. We do not use the actual observation goal observations by itself. We only use the hidden states. So the goal here is to get the states, the goal states at each time step be predicted by the prior preference model, right? So you can see that's on the top here is the real trajectory, and the bottom here is the actual dream. That's the dream of the robots that it wants to be, right? And then we are predicting that dream, right? So here is the actual model of the contrastive recurrent state prior preference learning. So basically, it has also similar architecture to the RSSM, to the world model. It also have an encoder Here it also have the transition, but it does not have the decoder. So how do we actually learn this um, prior preference model? So first of all, we learn the generative world model as normal, right? But when we say whenever whenever the trajectory is positive or a successful trajectory, um, we try to contract the state of the crispy. I just call it crispy. We try to contract the state of crispy to the world model state, and then um, whenever the um, trajectory is negative, we try to push away the states from each other so that the crispy model can only predict the positive states. So how do we determine um, if it is a positive trajectory or the negative trajectory without having a very sparse signal? So we will have a thing called raw or the prior preference signal. So how do we compute this raw signal? So imagine this is the real trajectory and it is a successful trajectory, for example, right? So we're trying to compute the prior preference rates by having the rates of the successful states is at 1, and it starts from 1, and then it decays backward. So it decays very fast, and if so in this like really far away states from here, they do not have enough signal because there's no goal like there's no direct goal from that states. And then there's real trajectory that is failed, right? You can see that the mountain car cannot reach the flags on the right here. So whenever it's failed, we can just flag, flag the very last observation as -1, and then we start to decay backward negatively. And then we have the prior preference rate signal as very negative. So the reason why it has to be last is because we want to blame the last observations hardest. So in order for the agents to just push away from the failing states very strong in the very last stage. So in the real trajectories that have like multiple successes, we try to put all the 1 in all the successful states and then just decay backward, as similar to how we would decay backward in a single success case. So with that said, we now know how to compute the rho, and then this will serve as the dynamic signal to the contrastive loss, and it creates a dynamic behavior of the contrastive loss that's trying to either push away or contract the two states of the crispy state and the world model state. So for example, in here, if there's positive rho, the contrastive loss would be contracting all the states together and maximizing the similarity between the crispy states and the world model states. And then we also learn to minimize the KL divergence between the complex, the posterior and the prior over the states of the crispy model. This is because we want to estimate the transitions, right? So we transition to the next goal state, and then this goal state has to match the actual goal. That is the current state of the RSSN model or the world model. So in contrast, right? If rho is negative, then we're trying to push away all these states away, right? So we're trying to maximize this distance or minimizing the similarity between the world model states and the crispy state. And in here, notes that there's no complexity objective is because we don't want to predict the next goal that is the failing state. That's basically the idea. So that arrives at the general formula for the objectives of the contrastive recurrent state prior preference model. Basically, it is just masking out the sign of the row and then multiply with the KL divergence or the complexity between the posterior and the prior of the crispy model. And then we minus the row and sim of the actual predicted state and the world model state. So sim here can be very much any kind of similarity functions, for example, cosine similarity. And then in our work, we actually use the actual cosine similarity. So in training time, we have just talked about training time, right? So we have successfully, assuming that we have successfully learned the crispy model that predicts the future goal. And in inference time, we use this crispy transition model to estimate future rollout trajectory of the goal, right? So we can see that on the top here is the observation, actual observations, and in the second row is the actual prior preference rollouts or predictions of the future goal given the current observation. So given the planned actions, we're also training the planned actions, right? So the actor trying to predict an actions given the observations, the predicted observation in the future. So we're trying to say we're trying to compare the actual prior preference rollouts with the actual predictions given the actions. And then we're trying to learn the action planner based on the signals or how diverged the future goal is to our future predictions of the world given the actions. So there can be so many reinforcement learning agents and active inference agents that can utilize this technique of prior preference learning. So active inference agents, I put my works here. It's RAIF, and then there's also Chris Buckley's work and Baron Smith's work about deep active inference in variational policy gradients methods, and also Otto work is the scaling of the active inference in POMDP and Norton-Carr environments, and so on, right? So reinforcement learning agents, there's all these sorts of actor predicts algorithms like Dreamer series, soft actor critic, dreaming, DDPG, TQC, and TD3, and so on. So there's a lot of agents that can utilize the framework because there's no change in the original architecture. There's just an add-on to how an agent would apply the prior preference learning signal into the system. So here's the actual flowchart of the agents. Basically, we start the agents, and for each episode, we evaluate the environment using the world model and the policy planner. Actually, basically, we evaluate in the environment. We let the robots play, we let the robots do the task, and then we collect the data and add them to the replay buffer, for example, right? And then we can get the main training agent logic. And then first of all, we sample the training data from the buffer. So in here, we trying to have, we also have to use the self-imitation learning buffer. So self-imitation learning is a very good technique normally to balance the number of successful and failing trajectories. And we also learned, so first of all, we learned the world model encoder decoder translation on RSSM. And then we train the epistemics model, but in this case, we don't need to care about it. And then next is the contrastive recurrent state prior preference model from the data. And then next, we imagine the future trajectory using the world model and the policy planner, right? We try to estimate the future actions to be what is the optimized future actions, for example. We estimate the future action based on how current state is, and then the world model will be continuing to roll out in the futures, and then we dream of the futures. And next is the part that we actually infer on the crispy model. We use a crispy model to imagine the future preference trajectory given the goal, given the current observations, and we predict the future goals, rollout goals, right? So after that, we learn the policy planner, right? Using the instrumental signal. The instrumental signals here is computed from the difference between the future goal and the predicted future dream of the world, right? And then with that, the policy planner can learn from the instrumental signal. So here's our preliminary results on active inference agent. So basically, we can see the two top rows is the mountain car environment, and the two bottom row is robotics meta world push button environment. So let's look at the first row, for example. The observation here is a mountain car that has reached the goal, and for each observation here, we predict a preference rollout or preference or a goal state at that single time step. So in here we can see that if the car has not have the momentum yet, then we have to build the momentum by predicting the car going to the left, for example, right? And then after it has built some kind of momentum, we're trying the actual prior preference model predicting the car would go to the right, go forward, right? When it goes here, and the prior preference model will predict the car to be going closer to the goal, something like this. So the same applies to the robots environments where the actual observation is the third row and the prior preference rollout is on the fourth row. So we can see that it is also trying to estimate the dream or the dream of the goal of the robots is to actually push the button. So there's different kind of experiment setup that we are trying to learn. Basically, we have 4 trials on each environment, and then we train the experts using soft autocritic or PPO, proximal policy optimization, to collect a small amount of seed data. Normally is about 20 episodes, something, 20 to 30 episodes. So we test mostly on 3 main environments or suits. First of all, is mountain car. There's only 1 task. Meta world is 13 tasks. So here's all red robots. Here's meta world, and then the robot suit we have 2 tasks. And then regarding camera setups, we use 3 views for meta world and 4 views for the robot suit. So the green check mark here denotes that the robot has successfully solved the task. Here's the robot suit, door, open door. And then here's robot suit lift, where it can successfully lift the block. And here's more solving agent tasks. So basically, agent with crispy exhibits an ability to perform successfully early on. So agent without crispy struggle to actually succeed on solving the environment. And we also test on our other environment as well. For example, gymnasium robotics and risk tasks. You can see in the middle image over here. So actually, we go to the discussion sections. So actually, I want to make a note that with respect to the crispy submodel, our model utilizes contrastive objectives to adapt its parameters. So basically, it solely learns on estimating the world model encoded states while pushing itself away from undesired world model states or trajectory. So this does not require the learning of the decoder. So we only make sure of the learned decoder in the generative world model to visualize the preferred observations from the estimated crispy states. So experimentally, we remark that this is an um, we only use this decoder to as an auxiliary tools to prove that the states of the contrastive recurrence prior preference model is useful. So theoretically, behavior cloning will be unable to achieve a great success in multi-goal environments due to its reliance on a fixed and finite size imitation sample pool. Um, the expert trajectory in this fixed pool might further differ from the actual trajectories that the agent needs to take to solve the problem at hand. For example, there's a distributional gap in observations, and therefore, it requires different sets of actions to be taken. For example, right? So on the other hand, right, Crispy learns to produce dynamically the goal states and not the goal observation, right? So we can empirically confirm in simulation that our agent with dynamic prior preference learning does not suffer from the goal mismatch problem in the training phase. So this is very applicable to the multi-goal environments. So we can see that this prior preference learning techniques has a lot of practical applications in different robotic tasks. With, for example, those with potential dangers in the operations and functioning. For example, when human safety must be considered, right? For example, trying to drive a autonomous driving car system where it has to have or it has to predict the future goal, right? The future goal is not to hit the human, for example, right? And we can also make a lot of advancement in imitation learning in research community, and it can be applied by the wide range of reinforcement learning and active inference agents. And then the last one is to scale the active inference agents on the real world robotics agents. So future words actually considered importing or integrating the dynamic prior preference learning in latent state space model, for example, variational dynamics, discrete variable autoencoders, or attention weighting models. And also, there's another models, physical neurorobotic system, which entails an embodied and active and survival-oriented formulations of active perception and world model learning. So in this talk, we have discussed a lot of ideas about being able to estimate the particular goal or preferred states at any particular time step is very useful for cognitive control agents. So as our results demonstrates, the agent can then learn to adapt to take actions that leads to a estimated goal. And then in contrast to the approaches taken in the imitation learning and behavior cloning literature, which train the agent's policy solely based on the fixed collected expert data sets in our framework, the expert signal is estimated dynamically through an adaptive prior preference model, right? Closing this gap, the domain gap between the actual trajectories and the collected training imitation trajectory or preferred trajectory. And then we also discussed the generative model and encoder decoder transitions and how the variational free energy work, and then how to learn the model. And then we discussed the contrastive recurrent state prior preference model with a self-revision mechanism, and then discuss the model learning and then inference objective, and how to integrate that into the agent's planar learning system. And then we show the results for the robotic task, and then mentions how it can be applied to different fields. So that concludes my presentation, and thank you very much for listening.
Thank you. That was amazing. Really great job with the background math. Done only like a PhD student can, but it was great to see how you brought it all together and connected your research to it all at the end. So, thank you. That's all for now. See you later.
Thank you. See ya.